So I'm going to record this, and I guess my first question. It seems like a very interesting subject, and I know we as humans have been able to directly measure carbon dioxide, for several decades. And then obviously we can use other methods like tree rings and ice cores to go back several thousand years, but you're trying to use mathematics to go deeper, right? Can you kind of go into how you are doing what you're doing and kind of what the importance is?
Sure, absolutely. So you're spot on about the tree rings, ice cores being a really useful tool for going back into the thousands of years ago range. We're going even further back to millions of years ago, all the way to about 500 or so million years in the past. And we're using proxies. That's what these tree rings and ice cores are, for temperature and CO2. So some of the proxies that we use are things like the densities of stomata, so these little pores in fossilized leaves. So these ancient leaves can give us some insight. Other proxies like cave speleothems, so things like just water dripping in caves and kind of building up. You can use ancient records from there to get a sense of what the CO2 and temperature have looked like millions of years into the past. And so we're using this modeling approach where we take our data sets for temperatures and CO2s, and we're looking at what kinds of the input parameters for, sorry, I've got a dog in the background there. And so we're looking at what, for our model, there's a set of input parameters. These input parameters represent kind of our knowledge of these geophysical processes, and out of the model comes CO2 and temperature estimates. And what we do is we're looking at what values of those input parameters represent the kind of observed or the proxy observations for CO2 and temperature well. And so we can rule out any kinds of parameters that don't match those proxy records.
So you basically kind of run a model, and then basically you can judge how that model performs based on the proxy. You kind of use it as an example and then run that model even further back beyond the proxies and kind of assume that that's generally correct, kind of, I guess.
So we go back to where the proxy records generally begin. So that's about as far back as we can go, is about 500 million years. And we have CO2 data getting back to about 420 million years ago, or I should say CO2 proxies going back to about 420 million years ago. And so we run the model from about that period to present.
So does it, I guess, fill in the gaps? I guess, kind of what's the goal, I guess, of why you guys are running the model?
Sure, absolutely. So one of the goals is to get some insight into what our current understanding of the Earth system, where we might be able to improve that. So one of the processes that's baked into this model is the way that different kinds of rocks are weathered. And so over the course of millions of years, you can imagine wind blowing over a rock and just gradually kind of wearing away at it, or rain falling on a rock and gradually kind of wearing away at it. And then some of these sediments coming off of these rocks, and in cemeteries, you can see kind of ancient like limestone, or well, not ancient, but old limestone starting to be weathered by these kinds of processes. And over time, all that sediment coming off of these rocks is making its way into rivers, and then those rivers are making its way into oceans, and kind of through ocean circulation and through tectonic plate movement, you might see these sediments kind of sifting or sinking their way down to the bottom of the ocean, subducting as these continental plates are moving. And again, this is not happening just overnight. This is over the course of millions of years, eventually making its way down to the mantle, where it gets kind of mixed up and it gets either vented out into CO2 into the atmosphere, or it can also be vented out through volcanic activity.
Mm-hmm. So you guys track are the two main things carbon dioxide and temperature?
Mm-hmm. And there's also oxygen, O2, being tracked in this model. Our study didn't look at that, but some other studies that are using the same model, we're also looking at oxygen.
Mm-hmm. And is the model run out of computers at RIT, or?
Yeah.
Because I know that, some of the weather models obviously takes a ton of computing power. I can imagine that it probably is the
Yeah.
same thing there.
Yeah, absolutely. So there's a kind of balance with models, that some of these models, especially for weather prediction, are extremely computationally intensive, and they're running over millions of individual CPUs using lots and lots of computer power, and a lot of that's for resolving things down to city-sized kind of weather events. And for our model, we're looking at just kind of global scale reservoirs for just kind of in bulk how much CO2 is in the atmosphere. And so we're not really resolving things like cloud processes. We're not resolving individual tectonic plates, just looking at kind of the global average over the course of millions of years. So there's a trade-off between the sort of resolution of individual processes that you're able to get versus doing kind of detailed statistics and uncertainty quantification, which was where we were focusing in this paper.
What are there any kind of initial takeaways from some of the early findings?
Sure. So one of the kind of key takeaways was this bias that in some of the previous work using this model during the Cretaceous period, somewhere around 90 million years ago, a lot of the time the model was kind of being seen to be a little bit cool relative to proxy observations for temperature. And so what we were able to do is run a really large set of simulations, thousands of model simulations, and figure out, based on varying the input parameters, each of which represents different geophysical processes, in what way did we have to modify those parameters in order to actually match the temperatures that we've observed through the proxy record over the past few 100 million years. And so that highlights a place where our understanding of how temperature has evolved and what processes contributed to that temperature, where we might be able to improve that understanding, and where there might be gaps where our records for, say, things like the river discharge into the oceans, maybe we need to do more research in that area, and that can lead to improvements in how our model can match prehistoric temperatures.
Mm-hmm. Yeah, and from my basic knowledge of climate change and the relationship between temperature and carbon dioxide, it seems like they're both pretty interrelated, right? You obviously get higher temperatures when you have more greenhouse gases, and then as temperatures go up as well, it's kind of like a positive feedback. Is that something that you guys saw as well?
Mm-hmm. So that's not something that the model explicitly resolves. It doesn't necessarily assume that there's a particularly that there's a one-to-one relationship. There are a couple of other factors that relate to the modeled temperature besides CO2. So things like changes in solar luminosity, for example, or changes in the continental configuration and the kind of total land surface area will also contribute to changes in the modeled temperature. So it's not necessarily a one-to-one kind of relationship, but there is definitely a relationship, certainly, that as CO2 goes up in general, all other things being equal, you see a rise in global surface temperature.
And is there, I know you guys have kind of looked back, have you guys done any looking forward? And because I know that 400 parts per million of carbon dioxide, that's a number we haven't really seen, obviously measured and then going back hundreds of thousands of years. Is that something that you guys are looking at as well?
So not necessarily in this work. In other work that I'm doing, a lot of it is related to things like coastal impacts and how that drives changes in, say, things like extreme storms or extreme precipitation. So there's some other work that I'm doing that is related to that. Here, there's a bit of a subtlety too, that we're looking at processes over the scale of millions of years. And so the kind of sensitivity that we're using to characterize that relationship between changes in CO2 and changes in global temperature, that's kind of averaging out over an extremely long, hundreds of thousands to millions of years. And then when we think about the timescale for kind of anthropogenic, for human-caused climate change, that's more on the order of tens to hundreds of years. And so there's a different sort of flavor. We call these things the sorts of climate sensitivities. And so the equilibrium climate sensitivity is the one for the kind of, next 10 to 100 of years that we're interested in. And we think of that as kind of a fast acting or a fast feedback climate sensitivity. And the one that we're looking at in this paper is related, but over a much longer time span. So we're thinking about lots of other processes that maybe for the fast feedback climate sensitivity just don't have a chance to show their head. Things like changing continental configuration. Not going to be one of the biggest concerns to humanity in the next 100 years.
Right. Yeah. So maybe in this model, you're not necessarily scoping out when there was a volcano launch, but more or less what it looked like over thousands of years type deal.
Exactly.
Right. Okay. Okay. That's pretty good. Is there anything else that you might, want people to know about some of the work that you guys are doing there that I missed?
I don't know. I think that it's a great approach because we're looking at trying to get a better understanding of how the Earth system works, and by doing this kind of a modeling experiment, we can kind of rule out just purely based on whether or not your model matches the data that you have available. We're able to rule out just completely implausible sets of model parameters or ways that it's plausible that the Earth system maybe worked millions of years ago, but then when you go back and compare the data, it just doesn't match the data. And so you get this kind of an inverse approach where you're working backwards to get a better understanding of these fundamental processes. And so that's kind of where this starts to link in to the more anthropogenic climate change side of things, that we just want to understand better how the Earth system works. And this gives us an opportunity to use information from the distant past to get insight into that. Just because, like you said, when we're thinking about 400 parts per million CO2, when we're thinking about just how quickly temperature has increased in the past few decades, that's something we have to go back thousands of years or millions of years to really get a good analog, back to ice ages, back to these large swings from greenhouse states on Earth to icehouse states on Earth. And so that gives us a better analog for what we're starting to see today in terms of really large swings in Earth's climate over fairly short kinds of time periods.
Okay, I think that's probably a good stopping point for me. Thank you for joining me